Newton's law of universal gravitation, part 2, gravity in space. Let's take a look at the formula for g, the acceleration due to gravity, that we had in the last lecture. Universal gravitational constant, mass of the planet involved, over r squared, where r is the radial distance from center of mass to center of mass. You're out here in space, in orbit. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Radius of the Earth, 6.37 times 10 to the 6th meters. And you want an orbit height. First, we got to get through the Kármán line. 100 kilometers up is nothing but air. If you try to achieve orbit speed, you'll go so fast that you will burn into a charcoal briquette in no time. Now, over that, let's have an additional 250 kilometers of orbit height. There we go. First things first, draw your picture. So not kidding. Draw the picture. Label everything. Label the mass. Label the radius of the Earth. Label the orbit height. Draw out RCM, the radial distance from center to center. Label it. Find it. Watch the units. Watch the units. Can't use kilometers. Can use kilograms. Pause. Draw. And when you're drawing this done and you're certain you know what RCM is, find G, the acceleration due to gravity. Press play to check your work. Ready? Found G? If you got 8.8 meters per second squared, you are in good shape. If you didn't, check those units in kilometers. Check for the squared in your denominator. Check for masses in kilograms, and check to make sure you're not typing times or 10 or to the anything. 5.98, capital EE 24, 8.8 meters per second squared. This begs a very important question. Is there gravity in space? Think about it. Think about it. 8.8 meters per second squared says yes! There is gravity in space. There's quite a lot of gravity in space. In fact, there's almost as much gravity in space as there is on Earth. Going up into orbit here has only made about a 10% difference. Next question. Are you falling? Look at your number. Don't shoot from the hip. Look at your number. Are you falling? Yes! You are falling at 8.8 meters per second squared. End of discussion. Does it feel like you're falling? No, it doesn't feel like you're falling. Why not? Well, we've been doing the problem so far for the space station. Now, what about the rocket ship at the same height? How fast is the rocket ship falling? Think about it. How fast is the astronaut falling? How fast is the astronaut's toolbox falling? How fast is the astronaut communication equipment falling? That's right, they're all falling together at 8.8 meters per second squared. So what do they see? They see the rocket ship, which is the same place relative to them as it always was. They see the space station, the same place relative to them as it always was. They see the toolbox, they see the communications equipment, they see all that stuff at the same place relative to them as it always was. It doesn't feel like they're falling because they're all falling together. Drop something, it won't go anywhere, it'll stay right next to you. Not because it isn't falling, but because you're falling too. You just didn't notice it. Think about being on a crowded train. If you're being pushed and jostled from all sides, how do you know the train is moving? Well, you look out the window and you see the platform speeding by, so clearly you must be moving. Or you see another train speeding by, which says clearly you must be moving. Or maybe you're at rest in the station and the other train is pulling out in the other direction. Relative to each other, nothing feels like it's falling because it's all falling together. Now in space, we've often said that you're weightless. Is this true? Well, G is 8.8 meters per second squared at this orbit height, so you've got plenty of weight. When we say you are weightless, we don't really mean weightless. Our sensation of weight, our apparent weight as we call it, isn't weight, it's normal force. We say you're weightless in space because if you stand on a scale, the scale won't read anything. Not because there isn't any gravity. The scale is falling out from under your feet because neither you nor it have any normal force. The normal force on you in space is 0, and so you feel weightless. In the first lecture, we talked strictly about numbers in Newton's law of universal gravitation. Big picture. What does this GMM over R squared mean? Newton's law of universal gravitation is one of the many inverse square laws that govern natural forces of the universe. Let's do a sample problem without numbers and see how we can figure out what the gravitational force looks like in our head alone. A satellite goes into orbit at a radial distance of r. There it goes. Round it goes. It has a certain weight, mg. G is no longer 9.81. G is now whatever the strength of the gravitational field is out here, gm over r squared. What will that satellite weigh if it moves out into a higher orbit at a distance of 2r? Do some work on paper. See if you can answer the question, not in letters, just in words. How much will it weigh if it moves out to a distance of 2r? Twice as much? Half as much? So show some algebra and show your work. Pause the video, work out an answer, press play to check your work. Ready? Well, the original weight of the satellite in orbit at a distance r, weight is just a fancy phrase for the gravitational force. There's the gravitational force, gmm over r squared. Now, at a distance of 2r, masses are the same. Universal gravitational constant, well, it's the universe, it's the same. And now the distance is 2r. What's 2r squared? If you said that out at this far distance the satellite feels 4 times less force, it weighs 4 times less, or 1/4 as much, you were right. If the satellite moves out to a distance of 2r, it will not weigh half as much, it will weigh 1/4 as much. And that's what we mean when we say inverse square law. Proximity isn't the only thing we have to worry about. It's proximity squared. If you go 10 times further away from a planet, you'll feel not 10 times, but 100 times less force. You'll weigh 100 times less. If you go 6 times closer in, you'll feel 36 times more force. You'll weigh 36 times more. There's a special vocabulary word for if you go there, what force will you feel? The question we've just been trying to answer. The word is force field. A force field answers the question, if you went there, what would you feel? The formula for force field for gravity is force divided by mass. Look familiar? Hey! Force divided by mass is also the same thing as acceleration. What a coincidence. The formula for G, the strength of the gravitational field, is gm over r squared. Why? It's the gravitational field that accelerates you down to the surface of the planet. Newtons per kilogram and meters per second squared, they're the same thing. This makes the question very, very, very easy to answer. Outside a planet, if you go 3 times further away, you'll feel a force that's 9 times less. Any number, square it, that's how much less you'll feel. What about inside a planet? If you were to go inside a planet, what would the gravitational field look like? What force will you feel if you go inside a planet? Let's go on Magic School Bus and find out. The difference between outside and inside the planet, besides, the rocks, the molten lava, and the pressures that are designed to vaporize you on the spot, is the question of where the mass is. When you're outside a planet, all the mass is definitionally below your feet, and it's all pulling in the same direction, namely toward the center, in this case, down. But once you go inside the planet, it's not true that all the mass is pulling you in the same direction. Some of the mass is now going to be above you. That's pulling you up. It's in the opposite direction of the mass below. You're going to feel less gravitational force here because 20% of the planet is above your head pulling you up and 80% is below pulling you down. Let's see, 20% up plus 80% down. Over here, you're only going to feel about 60% of the planet's gravitational pull. What about here when you get closer down? Now, 40% of the planet is above your head and 60% is below your feet. 60 down plus 40 up, you're only going to feel about 20% of the Earth's gravitational force here, that force is going to decrease and decrease and decrease as you fall until you get to the center where there's as much planet above you as below you, and you're not going to feel any force at all. The net force on you is going to be 0. Does this mean you will stop falling? Net force is 0. That means equilibrium. What kind of equilibrium is this? Pause. Think about it. Think about it. Dynamic equilibrium means you keep doing what you were already doing. What were you already doing? You were falling real fast. Just like air resistance, less force doesn't mean you fall more slowly, and it certainly doesn't mean you slow down. It means you don't pick up speed as fast as you were expecting to. You were expecting to pick up an extra 9.81 meters per second every second, and you did at the beginning, but then you found you were only picking up 8 meters per second, or 7 meters per second, or 6, or 5, or 4 meters per second every second, so that when you got to the core, if you hadn't been vaporized yet because of your cold-locked, pressure-sensitive magic school bus, you found you were falling very fast indeed, but not as fast as if you'd free-falled all the way down. You will keep falling, and now, once you keep falling, more of the planet's mass will be above your head, pulling up, pulling up, pulling up, slowing you down, slowing you down, slowing you down, slowing you down, until you get to China on the opposite side, and you find that by symmetry, you are at rest. You are, in fact, at rest over a giant hole that you just drilled all the way out of the planet, so you'd better have some nice Chinese friends in Miss Fri Zhao's classroom over there with wane ropes ready to pull you out so you don't fall right back in and do the same thing on your way up as on your way down.